Today, what I'd like to do is talk about population dynamics. And for those of you that are reviewing this, I am re-recording a lecture because I had stopped the recording and forgot to turn it on for class. So we'll basically go through the material that was covered during class. The reading assignment is Section 5-5. It's from Principles of Environmental Engineering and Science. It's a textbook that I wrote with Dr. Mackenzie Davis, who is a retired faculty member from Michigan State University. And I've provided that chapter for you in a folder called Supplemental Reading, and it's on Lon Kappa. Now, I'm reviewing these slides, as I mentioned, from class, so it's already amended with the notes from class. So population dynamics is the study of the changes in the numbers and compositions of individuals in a population within a study area and the factors that affect these organisms. And this population can involve any organism, from bacteria to humans, wolves on IRL, or bacteria in a biological reactor. The bacteria populations that we often talk about and that are important are within a reactor, so it's very important for the reactor design and operation. So for instance, in an activated sludge system, we need those microorganisms to metabolize the organic matter in order to produce an effluent that can be discharged to a stream. In a distribution system, we have biofilms. Those biofilms are on the inside of the hundreds of miles of pipeline that distributes surface water. We had a question in class about biofilms. Are they ever beneficial? Less so in a distribution system. However, biofilms are extremely important in wastewater treatment. Biofilms are important in membrane bioreactors. They're important in trickling filters, and we'll talk about this later, and also in rotating biological contactors. And again, we will talk about those towards the end of the semester. And then biological communities are important often in hazardous waste site remediation. Now, we looked at the growth requirements of microorganisms, and what is true also for microorganisms is also true for heterotrophic organisms all the way up to humans. So all organisms require a terminal electron acceptor, and that can be oxygen, nitrate, sulfate, or methane. And I've ranked them here in order of the energy that's obtained. So an organism that uses oxygen as its terminal electron acceptor will obtain significantly more energy per mole of that electron acceptor than an organism that uses methane. We group organisms by the electron acceptor. So an obligate aerobe, which includes us, so organisms that require oxygen to survive. Two obligate anaerobes, and those are organisms that cannot survive in the presence of oxygen. And then we have facultative organisms that can switch their metabolic activity between aerobic activity and anaerobic or anaxic environments. We also need macronutrients. These are the nutrients that are the backbone of protein formation, amino acid formation, carbohydrates. So carbon, nitrogen, and phosphorus are the three major ones. Number of students mentioned hydrogen. That is also, hydrogen is required in formation of these molecules. And sulfur is also important in some of the amino acids. We require micronutrients. These include trace metals. These can be calcium, magnesium, iron. All of these are important in metabolic activity. And then also vitamins. And then we need a proper, suitable environment. Temperature plays a significant role. Talk about mesophilic organisms. These are organisms that survive best between about 25 to 40 degrees C, and thermophiles survive at temperatures greater than 50 degrees C. Space. Organisms need space to grow. Proper pH. For instance, in an anaerobic digester, which is often used in municipal wastewater treatment to stabilize or to degrade the organic matter in the waste sludge, there are two groups of organisms. There are acid fermenters and methane fermenters. And if the growth of the acid fermenters is too great and they outnumber or outcompete the methane producers, what actually ends up happening is you result in a decrease in the pH to the point where the methane fermenters can't survive. And then you have what's referred to as souring of the digester because of the pH being too low. Now shown here, a bacterial growth curve for bacteria in pure culture. So note, this is for a pure culture. It's also for a closed system. So as I've noted here, and just think about this as we have a bacteria culture. Okay. We inoculate that culture with a organism, and what we see is an initial lag phase. So we've got this initial lag phase where the organism is acclimating to its new environment. As it acclimates, the growth rate accelerates. We have an accelerated growth phase. It then enters a log growth phase or an exponential growth phase. And then at some point, as shown here, what's happening is it's moving from the log growth phase to a stationary phase. So, for instance, the substrate becomes limiting. So it's running out of nutrients, or it's running out of the electron acceptor. It may be running out of space. Toxic byproducts may be building up. And also, when organisms become stressed, so it may be becoming stressed for these various reasons here, then it succumbs to disease, and disease organism proliferates, or disease proliferates. At this point here, we have stationary phase, and here the death rate is equal to the growth rate. And then lastly, we have a death phase where the death rate exceeds the growth phase. And where you see this point, this decline in growth, we can talk about that as the carrying capacity of the system. Now, with bacteria and many other microorganisms, they reproduce by binary fission. So one organism produces 2, those 2 produce 4, those 4 produce 8, and so forth. So we can describe that as a geometric progression where the population is equal to your initial population times 2 to the number of generations. Or we can write that in a logarithmic form, that log P is equal to log of the initial population plus n times the log of 2. So n is your again, the number of generations. So looking at this example here, during COVID, a lot of people have been really interested in fermentation processes. Sourdough bread making has become really popular. I'll admit, I've been making sourdough bread with my son all summer long. And other people have gotten into all sorts of other types of fermentation processes. So in this case, we have bread yeast, and that bread yeast cells form 2 cells every 5 minutes. So it's dividing every 5 minutes. If we place 10 to the 5 cells in a suitable environment, how many cells do we have in 30 minutes? So we have 30 minutes is the time. They're dividing every 5 minutes, so that means we have 6 generations. So the population after 30 minutes is equal to our initial population times 2 to the n, or 2 to the 6, and we would have 6.4 times 10 to the 6 cells. Now, rarely do we have a pure culture. Most commonly, we have a mixed culture. If you went to a wastewater treatment plant and you looked at the microorganisms in the activated sludge tank, you'd find a multitude of different organisms. If you looked at the microorganisms in a river, again, you would find a multitude of microorganisms, or same in a soil. Log growth may occur when one organism or one group of organisms has few external limits. So we can think, okay, when this mixed system, what affects growth? Well, here we have competition because we have different organisms. We have potential limit on nutrients, potential limit on oxygen. Because we have a mixed culture, we have a potential for predators. So for instance, in an activated sludge system, you would have, for instance, paramecium. The paramecium can eat the bacteria. So you've got a predator-prey relationship even in that type of a system. Ability to reproduce, or the reproduction time, plays a significant role. And then unfavorable physical conditions, and I described that before with souring of an anaerobic digester. The most successful species is the one that metabolizes substrates most completely. So it's the one that's gaining the most energy, therefore producing the most biomass, and it's going to outsurvive everything else. We can describe the dynamics of animal population with an exponential model. Important here is we're assuming infinite resources, so there's nothing to limit growth. And we can write that, as I've shown here, we can write it as a differential, that the change in the number of organisms with respect to time is equal to r times n. R is our growth rate, n is the number of organisms. We can integrate that from n sub 0 to n and from time 0 to time t, and that gives us this expression right here. So that is this expression right here, right here. And then we can take the log form of that and write it in this form. If r is positive, we have growth. If r is negative, we would have a decline in population. Now I've added this slide here this semester because in the news you hear a lot of information about R factors, and this isn't exactly the R, but it gives you a sense of the importance of what we're talking about when we talk with COVID as the R value. And I've developed this with a doubling time of 1 day. Now, we're not seeing with COVID a doubling time of 1 day. However, if we think back to March or April, in some cases we had a doubling time of somewhere between 2 to 4 days. So basically, if that were the case, just kind of expand the plot out. And what I want you to note here is, for instance here, if we have an R value of 1, okay, I've set this that n sub naught is equal to 1, and I've written this as the number of organisms is equal to n sub naught e to the r times 0.9693 t. So I've done that so that we have a doubling time of 1 day. So if r is equal to 1, we have a doubling time of 1 day. And what you see here is that after 10 days, we would have 1,000 organisms. So if you think of that back with COVID, if we have a doubling time, if you have one case and you had an R value of 1 and a doubling time of 1 day, after 10 days you'd have 1,000 cases. If the R value though is 0.9, we have half the number of cases. We only have 500. If it's 0.8, we would have 250 cases. If R is 1.1, we have 2,000 cases. So that R value, keeping that R value as small as possible is extremely important in the case of COVID, in order to make sure that our number of cases are manageable so that we don't overload hospitals, their medical system, and we can protect human health. Now, we can also use a geometric logistic model. Again, this assumes infinite resources, but in this case it assumes that growth occurs in discrete intervals, which is why I've used a bar graph here versus a scatter plot, because we're assuming discrete growth. So the equation is given here. So it's n at time t divided by n naught at 0 is equal to lambda times t. So lambda is our growth rate. If lambda is equal to 1, we have a stable population. If lambda is greater than 1, we have growth. If lambda is less than 1, we have a decrease in population. So again, this assumes infinite resources. It also assumes that the birth and the death rates is proportional to the current number of organisms. And we're assuming that we have no immigration or emigration, so we have a closed system. No gain or loss of organisms into the system. Now, obviously, there are limits. There's limits to growth. So what's been developed is a logistic growth model with a density-dependent limitation. And that's described by this equation here, where K is the carrying capacity. So the change in n, number of organisms with respect to time, is equal to R, which is our rate constant, times n times the quotient K minus n over K. So where K is our carrying capacity. And if we integrate that, we have this expression here. I've developed a set of plots for R is equal to 0.693. So in this case, I had a doubling time of 2 days. And we can see here, this is essentially, if we had infinite growth, I've actually set the carrying capacity to be 1 million. So for this situation, essentially that's infinite growth. And you see exponential growth. However, if I set the carrying capacity to 1,000, you see that after about 7 days, that curve starts to deviate. And you see that essentially it asymptotes at 1,000. If The carrying capacity is set at 250. We have this curve here. And again, it's going to asymptote at 250 because the system can't support, in this case, more than 250 of these organisms. Now, the Lotka-Volterra predator-prey model is a more complicated model, and it looks at the relationship between predators and preys. So what you see here, if we start at this point here, and we're looking here at the prey. So in the absence of a predator, population continues to grow, or if the predator population is low enough, it continues to grow. And the model will show that it grows exponentially in the absence of the predator. So you can think of the deer. 30 years ago, you never saw deer in neighborhoods. Now they're everywhere. And problem is there is no predator, or there are no predators in the area. So without the predators, they continue to grow. Now, as long as there are sufficient prey, the predator population grows exponentially. And eventually, there are a sufficient number of predators that the prey population decreases, and then lagging behind that, eventually the population of the predator will decrease. There's a number of other assumptions. For instance, that the predator will starve without the prey, that it has only one prey that it can survive on, and that the predators can consume an infinite amount of prey. So they have insatiable appetites. And we're also assuming that there's no complex environment or no environmental complexity, so that the populations are dependent solely on one another. But if we do this, it's actually a very interesting model that allows us to look at these relationships between predators and prey. Now with human populations, we potentially can use an exponential model. So in this case here, again, the population at time t is equal to the initial population, e to the rt, where r is the growth rate, t is time, and r is equal to a birth rate plus a death rate plus an immigration rate into the area minus the emigration rate from the area. And this is the population for Pima, Arizona. It looks like an exponential plot. However, if we only used the most recent data, it looks linear. So it's a question here of it's really important to think of the time. So in this case, let's look at the population of a number of cities, and we'll look at them over different time scales. So for instance, if we were to look at the population of Brighton, what we would see is that if we're looking at the population between 1970 and 2000, it looks quite linear with an R squared of 0.98. On the other hand, if we add the data for 2010, we see that there isn't significant change here. Now, let's look at Flint. So now with Flint, again, if we look at the population, in this case from 1900 to 1960, it looks linear. On the other hand, if we look at the population from 1970 to roughly 2010, what we see is that it is actually declining. So be very, very careful when developing these population predictions to consider the time scale that you're using. So during class, I put up this data, and we did a poll to look at what population model would best predict this data here. And you can see we have data for the decades from 1970 to 2010, and then we have annual data through 2018. So we can plot the data, and it looks like this. And in class, I asked whether the class thought the linear or the power function, exponential or polynomial fit, or the logistic model with limitations would best fit the data. And the results of the poll showed that the majority of students, actually about over 90% of the students, suggested that the logistic model with limitations would best fit this data. Let's look and see if they were correct. And here's the linear model. It's actually not a bad fit with an R squared, but you can see it really isn't modeling this current data at all. The power function does not work very well either. It's an R squared of 0.89, not bad, not great. Exponential model doesn't fit. The polynomial model does fit, and we actually have a very good fit with a second order polynomial. However, there's no physical relationship between the model and the actual system. And here we have a logistic model. So I've modeled this with a carrying capacity of 7,950 and a growth rate constant of 0.082. And you can see a very, very good fit of the data. And if we think back to the maps that I showed you on Monday, there wasn't a lot of space for growth within the community. And unless they started building high-density housing, there really isn't much room for growth. So it's not surprising that the city has a carrying capacity of close to 8,000. So from this, you should be able to list and describe the animal population dynamic models that we've used. You should be able to use those models. You should also be able to describe carrying capacity and explain how it influences population growth and use it in a logistic model. And then you should be able to discuss the question, do cities have a carrying capacity for humans? So thank you and have a great day.